This is Dr.D Govardhan, Professor in Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today the topic is the equilibrium of forces and related to problems. Here in a previous class, we discussed the resultant force. When the several forces are acting on a body, all the forces are replaced by a single force which will have the same effect of all the forces. Then the single force is said to be resultant of all the forces. If the resultant of all the forces is equal to 0, then the object is said to be under equilibrium. Condition for the equilibrium of a particle. In order to keep the body in equilibrium position, the resultant of all the forces which are acting on it should be equal to 0. But the procedure is, in order to determine the resultant of all the forces, according to the analytical method, resolve the forces into two rectangular components along the x direction, along the y directions. The algebraic sum of all the forces which are acting in x directions are treated as a resultant of x component of the resultant force. And if the body is in equilibrium position, that is also equal to 0 now. That means the sum of the component of forces which are acting along the x direction should be equal to 0. Similarly, after resolving the forces along the y directions, the algebraic sum of all the forces should be equal to 0. Or in other words, sigma fx is equal to 0. That is, sum of the component of forces in x direction should be 0. Sum of the y components also equal to 0. This condition is applicable if the forces are intersecting at one point. That is for the concurrent forces. The procedure now. Before finding resultant or the equilibrium condition of the body, first draw the free body diagram. The free body diagram is a sketch showing a particle free from surroundings with all the forces acting on it and showing external forces acting on it. When we are removing the supports such as surfaces, hinge support, pin support, ball support and everything, keep equivalent reactions offered by the support on it. Then write the equation for the equilibrium, that is sigma fx is equal to 0, sigma fy is equal to 0, and determine the forces of unknown quantity, so that the body should be in equilibrium conditions. Now I am taking one problem now. Okay, I am taking one problem here now. According to the problems, the body suspended 40 kg at a point A, which consists of two strings AB as well as the AD, so that the system is in equilibrium conditions. So, determine the tension in the strings as well as the strings, that is the AB and AD, which are shown in figure now. Since the body is in equilibrium position now, the sum of the component of forces which are acting along the x direction should be equal to 0, and also in the y direction should be equal to 0. So, the free body diagram is drawn in second case. Here the O is the intersection point at the concurrent where the forces are concurrent. The reactions within the string is always with respect to the reference point. This A point we have taken. So the reactions in the rope AB is always acting in the direction of AB, but away from it. Hence it is represented here O and B, but the arrow it is representing away from it now. Similarly, in the string AD, the force is acting toward the left side AD, the FT as shown in figure now. Now resolve forces along the x direction and y direction. Here that FB is there now, that is acting toward the right side and upward directions. The sum of the forces which are acting in x direction is equal to FB cos 30, since it is acting toward the right side, positive, minus FD, that is toward the left side, it should be equal to 0. By using these equations, we got the relationship between FB and FD, both are unknown quantities. Now take sigma Fi, that is FB sin 30, minus of 392.4 N, that is the weight, it should be equal to 0. By using the relationship, we got FB is equal to 785 newtons, and on substituting the FB in equation number 1, we got the values of FD, which is also equal to minus of 680 newtons. The negative is representing it is acting toward the left side. Now in second problem, in a coplanar force system, if the whole assembly is in equilibrium, determine the tensions in the cables DE, EA and EB for a given weight of cylinder 40 kg. Here the cylinder is now suspended, here it is representing 40 kg. But the system is under equilibrium position. There are coplanar forces, that means all the forces are acting in the single plane now. Now we are considering free body diagram for this problems by taking O as our reference point, E as the reference point. Now at E, the tension in the rope EB is always acting along the rope but away from the point E now. Hence, it is represented as T, E, B, that is the tension within the rope, and represented as T, E, B now. Similarly, in rope EAE, the weight is acting in downward directions, it is represented as T, E, A now. And ED, that is the horizontal force that is acting toward the left side, it is represented as T, E, D now. But we are considering at B, the pulley is weightless as well as frictionless. Hence, the tension in the rope on both sides should be equal. Hence, the tension in the TEB is always equal to that weight 40 kg now. So weight 40 kg means 40, that is the theta here M is given, weight is equal to, that is W is equal to M into G, that is the 40 into 9.81 newtons, here it is represented. That is the tension in the rope EB is equal to 40 into 9.81 now. Now applying equilibrium position for the system now. So the first step is first resolve the forces along the x direction and along the y directions. The component TEB is resolved in two components, one is the horizontal here now and vertical. This horizontal component is acting toward the right side, it is treated as positive, which is equal to TEB cos 30, and TED is toward the left side. So according to the equilibrium conditions, sigma Fx, that is sum of the forces which are acting along the x direction, is equal to TEB cos 30 minus TED, it should be equal to 0. Hence, from this relationship we got TED is equal to 340 newtons. Similarly, sigma Fi is equal to, that is sum of the components which are acting along the y directions, it is equal to, that is the weight TEB sin 30, that is the 40 into 9.81 sin 30, that is acting upward direction positive, minus TEA, that is force which is acting along the AE rope, acting downward direction, theta is negative, it should be equal to 0. By using this relationship, we got TEA is equal to 196 newtons. Since the system is in equilibrium position, so under the actions, we can determine what are the forces that are acting within the rope to avoid the failure of the strings by the analysis of forces. And one more problem. The boxes 550 Newton and geometry shown in figure determine the forces in the ropes AB and AC. It is similar to the previous problem only. In this figure, the load is acting vertically downward directions. The tension in the rope AB is along the AB directions. Within the rope AC along the direction of the rope AC, which is shown in figure. First, draw the free body diagram with O as the reference point we have taken. Here, the important reference point is to locate the tension within the rope. With respect to the A, the tension in the rope C is acting along the rope and away from it now. Hence, it is represented here now. A, C, and represented FC away from it. Similarly, between AB, it is represented as FB away from it now, making an angle of 30 degrees. Here, 4, 3 is given this inclination now. It is nothing but the meaning is it is a right angle triangle if you take. That is, 4 is representing adjacent side and 3 is representing opposite. Hence, 5 is representing hypotenuse now. Now, it becomes sin 30 is equal to, that is according to this one, sin theta is equal to 3 by 5, it is equal to 0.6. Cos theta is equal to 4 by 5, which is equal to 0.8 and so on. So, this is nothing but useful for determining the values of sin theta, cos theta and tan theta and so on. Now, for resolving the forces FC and FB, we take horizontal line here now from A, horizontal lines and vertical line. This vertical line is moving upward direction, the horizontal line moving towards the right side. These two components are treated as positive. Similarly, in FB, this force we need is resolved in two components. The horizontal component is moving towards the left side and the vertical component is moving upward directions. Hence, the vertical component is positive and horizontal component is negative. The weight is acting downward directions, hence it is treated as negative. Now, applying equilibrium conditions for this system of forces, we got sigma fx is equal to, that is sum of the component of forces which are acting along the x direction. It is equal to FB cos 30 positive minus FC into 4 by 5. It should be equal to 0. The second one is the sum of the component of forces which are acting along the y direction is equal to FB sin 30 upward directions minus 550 newtons downward directions. It should be equal to 0. On solving these two equations, we got FB is equal to 478 newtons and FC is equal to 518 newtons. Equilibrium now. Sometimes when the forces are acting on it, the single force which will keep the entire forces in the equilibrium position is treated as equilibrium. It is always equal to the resultant force but acting in opposite directions. The general condition for the equilibrium for the non-concurrent and coplanar forces is given by sigma fx is equal to 0, sigma fy is equal to 0 and sigma m is also equal to 0. Where sigma m is representing the moments created by the forces at a given point. For concurrent forces, the sigma m is not valid equation. The modified equation is sigma fx is equal to 0, sigma fy is equal to 0. And one more problem we are taking. Determine the tension in the rope TBC. Okay, in this problem, the lamp is hanged vertically downward directions with the ropes AC and BC shown in figure. The weight of the lamp is given 15 newtons. These problems can be solved by using two methods. By using Laplace equations and again by resolving the forces along the x direction and y directions. Now, according to the geometrical relations, now this angle now becomes, if we resolve here 45 degrees, that is if I draw the figure, that is AC is acting downward directions. The weight is given 15 newtons. C point. ACA is given. The angle is given with the horizontal 60. And this angle is 60 is given. Here it can be resolved in two components, toward the left side and upward directions. This force is represented by C and it is the A. As it is the TCA, that is the tension now. Similarly, in BC, it is represented at TBC. The inclination now becomes, it is a 45 degrees. And when it is resolved, it is there toward the left side and upward directions. Now it is nothing similar to the previous problems. First we resolve the forces along the x direction, along the y direction. Take sigma fx is equal to 0, sigma fy is equal to 0, and we can determine the forces. In the second method, Laplace method, we identify the forces directions with respect to the C point, CA and CB, and weight 50 newtons. The included angle is 75 degrees between AB. Between A and weight, that is given 150 degrees. And between weight and B, it is given 135 degrees. According to the Lami's principle, when the system is in equilibrium position, each force is proportional to the sine of the angle between the other two forces. That means here 15 divided by sine 15 degrees, sine 75 degrees, which is equal to TAC divided by sine 135 degrees and TBC divided by sine 150 degrees. So, on solving these equations, we got to TAC is equal to 10.98 newtons. Similarly, TBC is equal to 7.76 newtons, which is shown in figure now. Now, I am taking one more problem now. A light string ABCD, whose extremity A is fixed, as a weight W1 and W2 attached at B and C as shown in figure. It passes around a small smooth peg at D, carrying a weight of 300 newtons at the free end E as shown in figure. Since the pulley is weightless and frictionless, on both sides of the pulley it is having the same tension. If the system is in equilibrium position and BC is in horizontal and AB and CD makes 150 and 120 degrees with the BC, now find tension in the portion AB, BC, CD and the magnitude of W1 and W2. Now at C, when we are taking, at C, drawing this free body diagram, at C, the weight W2 is acting in downward directions, W2, the tension is there, TCD. Its inclination is with respect to the horizontal, it now becomes 60 degrees. And BC is also again horizontal now. T, B, and C now. But TCD, other side, it is having 300 newtons. Since according to our problems, the pulley is frictionless and weightless, hence the tension on both sides should be equal. Hence TCD is equal to now becomes 300 newtons. Now resolve the forces along the x direction and y direction now. From this relations we got to TCD into sin 60 equal to W2. Similarly, TCD cos 60 is equal to TBC. By using the relationship, we can determine the tensions within the rope CD as well as the BC now. Now, the same here represented now. The weight E is equal to given 300 newtons. For the sake of convenience, split the string ABCD into two parts. The system of forces at joints B and C shown in figure now. The tension in the ropes AB, BC, CD. Here TAB is representing tension in the rope AB, TBC represents tension in the BC, and the tension in the CD and DE both are equal, hence it is equal to 300 newtons. Applying Lewis principle, or you can resolve the forces in x direction and y directions. According to the Lewis equations we got, the Lewis principle is representing when the system is in equilibrium, when the three forces are acting at a point, and if they are in equilibrium position, according to Lewis principle, each force is proportional to the sine of the angle between other two forces. That means TBC divided by sine 50 degrees, W2 divided by sine 60, which is equal to 300 divided by sine 90 and so on. So on simplification we got W2 is equal to 259.8, TBC is equal to 150 newtons and so on. So we can resolve this problem by using sigma fx is equal to 0, sigma fy is also equal to 0. Now at B, before applying B, just I will give the explanation regarding resolve the forces at B. Okay, at B, the BC force is an horizontal now, away from a point B. Already we determined these values by taking equilibrium position at C. The weight W1 is acting downward directions, is given, and angle is given here. Here the tension in the rope TAB, it is making an angle of 30 degrees with the horizontal. Now resolve the forces into two components, vertical and horizontal. Now sigma fx is equal to 0, fx is equal to TBC is a positive minus TAB cos 30, it should be equal to 0 required now. Since the TAB already we determined, TBC already we determined, by using the equations we will get the values of TAB. A second equation is sum of the forces which are acting in vertical direction. So that W1 is sigma Fi, it is equal to W1 is acting downward direction, so negative, and the component of forces of TAB is acting upward direction, so hence TAB sin 30, it should be equal to 0. By using the relationship we will get the values of W1. Hence, these problems can be solved by using resolve the forces along the x direction and y direction, that is analytical method, or by applying Lami's principle. Now, according to the Lami's principle, now let B, BC is already given, TAB is given, the included angle now becomes 150, it is given 90 degrees, total 360 is required now. So the remaining angle now becomes here 120 degrees now. Now, according to Lami's principle, TAB divided by sin 90, which is equal to W1 divided by sin 50, which is equal to TBC divided by sin 120. Since TBC already we determined which is equal to 150 newtons, and substituting the values of TAB divided by sin 90 is equal to 1, which is equal to W1 by sin 150, which is equal to 150 divided by sin 120. On simplification, we got TAB is equal to 173.2 newtons and W1 is equal to 86.6 newtons, which is shown in figure. Hence, the magnitude of W1 W2 are 86.6 and 259.8 newtons respectively.
Like, share and subscribe. Hit the bell icon for more updates.